Hello everyone. Okay, this is mechanics of material, and here I'm going to show you another example for the internal force calculation. Is from your homework problem. Okay, so this is a homework problem. There is a beam placed on a certain support, AB support, and there are some external loading, 6 kN pulling down, and there is a distributed loaded acting on this beam. Okay, and problem want to calculate the internal force on section C and section D. Okay, for this type of calculation, we know we have to cut a section on the C or cut a section on D and do the force balance, moment balance, and calculate internal forces. Okay, but if there is some reaction from the support, so first of all, you also have to calculate the reaction force from this support. Okay, and then do the force balance on section C and section D. Okay, so there's some support. First of all, you need to do a global rigid body equilibrium to calculate the reaction force or reaction moment from this support. Okay, and in this problem, it's very nice. Okay, it already tell you this support only has a vertical reaction force. That means A and B support, they want to reacting they only had reaction force point up. Okay, we assume the point up. Sorry. So there's a reaction force here point up, so it's AY. I call it reaction force from B is called BY. Okay, so first of all, we need to find out AY and BY first, and then do the calculation on section C and section D. So first of all, we have to do the global rigid body equilibrium, rigid body equilibrium. And how to do that? Okay, so we do the equilibrium. First of all, we need to draw the free body diagram. Okay, let me treat this beam as a straight line. Okay, and much easier to understand. And we already have AY and BY. This is a reaction force and support. And we have external loading. Let me see. We have the external loading, 6 kilonewton point down. And this is, he give a distance here. Here is a 0.5, and here is another 0.5, and here is 1.5 and 1.5. And here is from this here, will be a distributing loading. Okay, distributing loading. Okay, and we want to do the global rigid body equilibrium. We have to make a simplification of this distributing load. Okay, because distributing load, you cannot do this calculation directly, so you have to make a simplification. So you have to make a simplification of distributing loading. Okay, and this distributing loading, so the area is just right triangle. Okay, so what's the resultant force of the distributed loading? Okay, just area under this curve. Okay, the area of this right triangle is very easy. Okay, let's us calculate. FR is 1/2, and here is 3, and here I think it's also 3. So 3 times 3. So it's 4.5 kilonewton. I think it's point down. And where is the position of this resultant force? Okay, the centroid, I think it's probably here. And what's the distance here? It's the centroid of triangle. There's a common sense in the mechanical and engineering calculation. So distance here must be 3 divided by 3 equal to 1. So here is 1. Okay. So let's see. Okay, I think the resultant force is right probably here. Resultant force is here, and the distance here is 1. Okay. Okay, so distance here is 1. Okay, so and FR is equal to 4.5. Okay. Okay, and it's kilonewton, don't forget. Okay, and then we can start to do the rigid body equilibrium. Okay. Rigid body equilibrium. Okay, how to do this type of calculation? Okay, sigma fx equal to 0, and we check there. Yeah, there is no force has x component. So yeah, okay, and fy equal to 0. Y component force is equal to 0. So so let's see. We have ay point up. and 6 point down, and resultant force 4.5 is also point down. Okay, and we have by assume point up and totally equal to 0. Okay, and we see, can we solve this equation? Yeah, we cannot solve this equation because two unknown, we only have one equation, so it's not solvable. Okay, and so we have another final equation is the moment equal total moment of the system equal to 0. And which reference point you want? I can choose A as a reference point or choose B as a reference point. No matter which reference point you choose, you are choosing, you will get the same answer. And let me see what's my choice. Let me see my script. I choose B. I choose B as a reference point. Okay, for calculating the moment. Okay, B is here. Okay, B is here. So let's see. Okay, AY will cause a moment with respect to B. Okay, and what's the magnitude? Okay, it's AY, and what's the labor arm? Is 0 0.5, 0 0.5 is 1, and plus 3, so it's 4. And the force is point up, and the reference point is here, so it will generate a counter. It's a generate clockwise rotation, so it will become negative. And 6 point down. Okay, and the reference point here, so it will generate counter clockwise rotation, so it will point up. So in 6 and times the labor arm is 3 plus 1.5 plus 1.5 plus 0.5, so it will be 3.5. And the resultant force here, so reference point here, so it will generate a counterclockwise rotation. So counterclockwise rotation is positive. And what's the labor arm? Be careful what's the labor arm, because the length here is 3 and here is 1, so the labor arm here is 2. Okay, don't forget, be careful for the labor arm. So, and we choose a reference point at B, so we don't have to calculate at the moment caused by the BY, because BY is acting on the reference point. Okay, so that was from any moment. So, and it's equal to 0, and then you can find, use this equation, we can solve the AY. So the AY is, I think it's AY. Let me see, is my equation correct? Minus 4AY plus 6. Yeah, it's correct. So you will get AY is equal to 7.5 kilonewton. Okay, and if you have AY and then you can put this in equation, you will get the BY is equal to 3 kilonewton. Okay, just use your calculator and calculate by yourself. Okay, so we have a reaction force. For reaction force from support AY and BY, AY is 7.5 kilonewton and BY is 3 kilonewton. Okay, and after you get this information, and then you can calculate the internal force on section C and section D. Okay, so we start to calculate a section C. Okay, looks like section C is much easier to solve. Okay, and then let me erase this information here. So, okay. So global rigid body equation, I still leave the information here, but I think after minutes later, I will still have erased this information. So we start from calculate internal force on section D. If you cut a section here, okay, when you cut a section, you have to choose you calculate from the left or calculate from the right. Okay, and no matter which from the left, calculate from the left or calculate from the right, you will have to get the same answer. I keep continue stress this. Address this point. Yeah, no matter you calculate from the left and calculate from the right, you have the same answer. So the only thing you have to consider which side is much easier to solve. Okay, so for the section C here, if you calculate from the right, you have to deal with this distributing load, and the reaction force here. And if you calculate from the left, okay, then you calculate from the left, that means you can ignore everything from the right. So you calculate from the left, you can ignore this distributed loading. Okay, so and from the left, you only have these two reaction force only, so it's much easier to calculate. If you want to calculate internal force at section C, it's way much easier to calculate from the left, right? So when you choose which side, you have to choose, you have to think which side is much easier to solve. And so in this problem, I choose to calculate from the left, okay? And calculate from the left, we have the reaction force. Oh, sorry, I think I should use we have the reaction force AY here, and we have, sorry, this is too, sorry, I draw this, I think it's too short, okay? Okay, let's redraw this. We have to calculate from the section C. We calculate from the left is section C. Okay, and we have reaction force here, AY. We already know it, 7.5 kilonewton. And we have 6 kilonewton point down. Okay, and this distance here is 0.5. Here is 0.5. Okay, and okay, internal force here. Okay, we can just assume internal force here. We have what do we have? We have a shear force, normal force, and the reaction moment as C. And then we can do the rigid body equilibrium to solve VC, NC, and MC. Okay, so how to calculate this? I think it's very easy. Okay. Let's start right here. Summation fx equal to 0, and you see we have only x component is nc, so nc is equal to 0. Okay, yeah, nc is equal to 0, and summation fy also equal to 0. Okay, summation fy equal to 0. How many y component force we have? Okay, we have ay point up and 6 kilonewton point down, and a VC initially we assume it's point up. Okay, we have these three forces on the right point to y direction, so we have to write it down. Okay, so it's AY point up minus 6 and minus plus VC equal to 0, and AY we already know is 7.5 kilonewton. So if you put an answer here, so you have VC will equal to minus 1.5 kilonewton. Okay, and be careful, the VC minus 1.5 because we initially assume it's point up, and we get a minus answer here. That means the direction of this shear force is point down. Actually, is point down. Okay. Okay, here I think I have to erase this information here. If you still want this information, just rewind it. Okay, I have to erase this part. Sorry. And the final one is the moment. Okay, is the moment. Okay, we have to calculate the moment as C. Okay, so we still choose. So we just choose the C as a reference point. We choose C as a reference point. Okay, summation MC equal to 0. Okay, we choose C as a reference point. Okay, okay, so AY will cause the moment on the C, at the reference point C. So it's AY, okay, times the labor arm is 1, okay, and it will create a clockwise rotation, right? Clockwise, okay, because the reference point I see will create clockwise rotation, so it will become a negative. And here 6 kilonewton, this force will create a moment with respect to C, and it will create a counterclockwise, so it's positive, and 6 times 0.5. And at a C section, this section has a moment, and we assume it's positive, counterclockwise, and we still have to write it out and close to 0, overall equal to 0. So okay, what is A1? We already know A1 is 7.5 kilonewton, so it's minus 7.5 plus 3 plus MC equal to 0. So MC moment as the section C will 4.5. Don't forget its answer is kilonewton times meter. And we assume it's counterclockwise. Okay, initially we assume it's positive, and then we get a positive, and that means it's really positive. So it's a counterclockwise. Okay, so let's internal force at C. NC is 0 and VC is 1 minus 1.5, but it's point down. It's point down. Okay, let me see. And also 4.5 kilonewton times the meter, and it's positive. It's counterclockwise. So that's the internal force at C. Okay, and 17 want to calculate the internal force at C. C is a little bit more difficult, but I think it's still the same. So I have to erase this information out. So just please, if you want to take some notes, just please stop and rewind, or because I have to erase all the information out. Okay, sorry, because I want to reduce the time of the video. Okay, so for the section, section D, okay, which way? So if you cut the section D, you want to calculate from the left or calculate from the right? For the section D, you want to calculate from the left or calculate from the right? So if we cut a section at the D, for example, okay, we cut a section at the D here. If we calculate from the left, we have this distributing loaded, okay, and this is external load, and this reaction force here. And the distributing load, if you calculate from the left, the distributed load, then this will be a trapezoid. Okay, and we already know if you have a trapezoid distributing load, then it takes more time to do the calculation. But if you calculate from the right, the distributing loading is just a right triangle. So it's much easier to do calculation, and only one reaction force here. And from the left, there's a trapezoid distributing loaded and the reaction force and external force here. And from the right, you calculate from the right, only one reaction force, and on the distributed loading is a right triangle. So based on this information, I think you should choose the calculate from the right. Okay, calculate from the right is much easier to solve. Okay, I hope you can understand why I choose calculate from the right. Okay, and the calculate from the right. Okay, let me see. We have a by, and by you already know it is 3 kilonewton point up. And we have distributed loaded here. We still have distributed loaded, and if you calculate from the right, so you still have faced the distributed loading, but it's much easier to calculate. Okay, and anything else? No. Okay, and we have some internal force as this D section. We have a VD. We assume V shear force, normal force, and the moment here. And if you want to do so we have to use the rigid body equilibrium to calculate VD, ND, and MD. Okay, but before that, you have to make a simplification of distributed loading. Okay, and because these right triangles are much easier to do the simplification. But if you calculate from left, you have to make a simplification on trapezoid distributed load. Okay, that's much more difficult. So if you calculate from the right, okay, now first of all, okay, if you want to calculate the resultant force of this distributed load, first of all, you need to know where is this point. Okay, here the total distributed load is here. Okay, the total is like this. The total is like this. Total distributed loaded is here, is 3 here, and here is 3. But right now, here we only have the 1.5, right? Because we cut section here is only 1.5. And we want to know what's the force intensity here. And here is 1.5, and yeah, maybe rather drawing scale. Okay, here's 1.5, 1.5. Okay, here's 1.5, here's 1.5. So what distributed load here? Okay, so you can use a similar triangle that 1.5 divided by 3 equal to the question mark divided by 3. So this is 1 over 2. So the question mark will become 1.5. So here is 1.5. Here is 1.5. Here is 1.5. Okay. And you know here is 1.5, and then you can calculate the resultant force of this right triangle. Okay, so what's the resultant force here? Is this right triangle? Okay, and known as 1 over 2 times the height 1.5 and times its base here is also 1.5. So this is a resultant force. Okay, this is a resultant force on this area. Okay, and what's its position? I think the resultant force is centroid of right triangle. So the centroid of right triangle, I think centroid is very close to here, and with a resultant force, and the distance here is 1.5 over 3. So I think this is 0.5. Okay. So we know the position of this resultant force. Okay, we know the magnitude of resultant force and the position of resultant force, and then we can do the three-body equilibrium to find the ND, VD, and MD. Okay, let me just erase this. I just use the result of the simplification. Okay, the resultant force is here. Okay, Fr. Okay. And the FR, I think it's 1 over 2 times 1.5 times 1.5. So the magnitude resultant force is, yeah, I think use your calculator to calculate. Let me see. It's 1.125 kilonewton. And position here is 1.5 divided by 3. So here is 0.5, right? Yes, right. Okay. Okay, so let's use a rigid body equilibrium and get the answer. Okay, summation fx equal to 0, so minus nd, and yeah, we have no other x component force, so nd is equal to 0. And summation fy is equal to 0. Let me see. We have a shear force at D point up, so positive, and resultant force 1.125 kilonewton point down, so it's minus 1.125 kilonewton point down. And we have reaction force By point up, and By we already calculated 3. So okay, that's why you need to do the global rigid body equilibrium to calculate the reaction force from support. Okay. So we will have equal to 0. So we will have a VD is equal to minus, I think it's minus 1.875 kilonewton. And okay, and because initially we assume the shear force is point up, but we get a negative answer, that means its real direction is point down. Okay, real direction is point down. Okay, and okay, so the final one, what's the moment at D? For the moment at D, we just choose D as a reference point. Okay, so I write it here. Summation MD equal to 0. Okay, we choose the MD as a reference point, and there's a moment at the D section D, so we still have to write it out MD. And this resultant force will cause the clockwise rotation with respect to D. So the FR 1.125, and its labor on the reference point is D, so labor on is 0.5. And it's the clockwise rotation. So it's negative. And here the By will also cause a moment with respect to D, and it's counterclockwise. So you have the By is 3 and times 1.5. So in the counterclockwise, and then equal to 0. So you will have the MD. I think that's the MD, right? Yeah, that's the MD you have. Okay, let me see. The MD minus 4.5. Okay, And then you'll get the MD. What's the answer? I just write the answer here. You will get finally you will get MD equal to minus 3.9375, and it's kilonewton times the meter. And we get a negative value. That means because initially we assume it's counterclockwise positive, okay, but we get a negative value. That means the real answer is clockwise rotation. Okay, so okay, so that's the internal force at section D. Or normal force equal to 0, shear force point down, and the moment is the clockwise. So I think that's the answer of this problem. Okay, so okay, here's your homework problem to calculate internal force. I hope you can familiar with that. Okay, that's very basic skill in this course. Okay, so I just stop the video here. I think this video is kind of too long, so see you in the next video. Bye bye. Yeah.